To reduce our carbon emissions globally, the clean energy movement has gained substantial momentum within the past few decades. Technologies like wind, solar, and biomass often are considered in place of traditional energy generation systems. The biological waste-to-energy technology known as anaerobic digestion is one of these clean energy technologies that has found success on many different scales. Whether we range from small-scale systems on rural farms in the global north or even the global south, to even larger-scale centralized systems that are in process recovering resources from many different kinds of waste streams. But first, let's talk a little bit more about anaerobic digestion.
Anaerobic digestion is a process in which microorganisms stabilize and degrade organic material under anaerobic conditions. Biogas, stabilized biosolids, and liquid waste are the main byproducts of the process. Anaerobic digestion is a natural process that occurs in living things and in soils and sediments as microorganisms that favor anaerobic conditions degrade organic matter. Engineered anaerobic treatment processes can be used to treat industrial wastewater, municipal wastewater, livestock wastewater, and food waste. The biogas produced during anaerobic digestion can be transformed into electricity or distributed into the natural gas pipeline. The biosolids produced from the process can be used as a soil amendment, therefore contributing to the biogas cycle. Compared to other treatment processes such as aerobic treatment, anaerobic digestion produces a stabilized effluent that can be used as a soil amendment. Anaerobic digestion does not require aeration and thus reduces cost. This system produces energy and has low biomass production. In addition, anaerobic digestion microbes have low nutrient requirements and can effectively treat hazardous compounds. Anaerobic digestion does, however, have some disadvantages. Anaerobic digestion requires different groups of microbes that require different temperatures, pH, and operating parameters. Methanogens, biogas-producing microbes, are sensitive and slow-growing. Corrosive gases such as hydrogen sulfide can also be formed, and the effluent needs further treatment due to production of ammonia. As shown in this diagram, anaerobic digestion requires about 4 processes to effectively produce biogas. Each step is performed by a group of microorganisms with different requirements. Therefore, operating and performance parameters must be monitored to ensure a smooth syntrophic relationship between the microbes within the system.
Within the developed world context of anaerobic digestion systems, there are several scales that can be evaluated to better understand how anaerobic digestion works. Ideally, no matter the scale of your anaerobic digestion system, there are certain performance and operation parameters that are considered on all levels in order to ensure a well-functioning system. Here at the University of South Florida, we are operating both pilot scale and bench scale systems in order to understand how these anaerobic digesters function. There are several activities that are associated with the operation and maintenance of anaerobic digesters. The collection of waste is very important, as is the preparation of a consistent feed. Overall, numerous operational tests such as ammonia concentration, volatile fatty acid concentration, and the biogas production are often monitored to ensure well-functioning systems. On this small laboratory scale, a lot of attention is required in order to maintain these individual units. But let's see what happens when we look at the larger scale.
With the enlargement of the European Union, the accession countries are coming under pressure to develop and meet European Union standards for environmental protection and sustainable development. In this ongoing process, global economic liberalization, regulatory policy, conservation, and lifestyle issues are all involved, and creative solutions will have to be found. In addition, in the last decades, the goals of wastewater treatment have become ever more ambitious, and thus the technologies used are ever more sophisticated. The result is that both the energy required for and consumed by the treatment processes has risen. Simultaneously, the minimization of energy consumption has become a major goal for wastewater treatment plant operators. Integrated water and energy systems have therefore become fundamental to social, economic, and environmental well-being and prosperity for both developing and developed world wastewater treatment system. Optimization of total energy consumption during wastewater treatment and application of anaerobic digestion technology have become essential in improving the energy balance in municipal wastewater treatment plants. Generally, the easiest way to increase biogas production and thus improve the energy balance of a wastewater treatment plant is to supply an external organic carbon source. However, this increases the cost of operation. The Prague wastewater treatment plant in the Czech Republic is an ideal example of a municipal plant that has focused on developing an energy-sufficient, energy-neutral wastewater treatment facility. The Central Wastewater Treatment Plant of Prague treats wastewater from Prague's 1.5 million inhabitants. The plant began operation in 1967 and is located on an island in the Vltava River. Today, the plant's large treatment facilities consist of 12 anaerobic digesters. Each digester has an operational volume of 4,800 meters cubed, operated at a thermophilic temperature of 55 degrees Celsius with a solids retention time of 25 days. To intensify their energy production, the Prague wastewater treatment plant adds iron and aluminium salts at the beginning of the process to enhance removal of carbon, thus increasing biogas production. The operators also thicken the wastewater influent to increase the loading rate and have an enhanced digester mixing system to improve contact between the substrate and anaerobic microorganisms. The enhanced anaerobic digestion treatment system produces 0.63 meters cubed of methane per meter cubed of digester volume per day. This is about 50% greater biogas production than what other typical municipal wastewater treatment plants achieve. Such an elevated level of biogas production is sufficient to cover a large part of the total energy demand of a wastewater treatment plant. In the specific case of Prague Central Wastewater Treatment Plant, the self-sufficiency rate could even be higher. However, due to the low capacity of the combined heat and power units, only 92% of the produced biogas is actually used to generate electricity. Before the biogas is converted into electricity, removal of hydrogen sulfide to levels below 50 parts per million is often required for reasons of health, safety, environment, and corrosion of equipment such as gas engines, boilers, and piping. Desulfurization is also necessary when biogas is upgraded to natural gas quality and injected into a grid. For safety and during emergencies and maintenance, controlled burning of the biogas, flaring, is performed. Biogas is about 60% methane, a clean burning fuel. However, methane is also a greenhouse gas. Therefore, in situations where capturing the gas is not possible, it is better from an air quality perspective to ban methane and convert it into carbon dioxide through a flare system rather than vent it directly into the atmosphere. This is because methane has a higher global warming potential compared to carbon dioxide. Obviously, maximization of biogas and electricity production is a major task on the road to energy self-sufficiency. However, equally important is the utilization of nutrient-rich biosolids. About 50% of the biosolids produced at Prague's wastewater treatment plant are composted, 17% are land applied. The percent of land application has decreased due to concern of heavy metals and pathogen content in the biosolids. Biosolids of insufficient quality, about 13%, are sent to landfills.
We'll talk more about the safe use of the residual in a moment, but first, let's focus on developing world systems.
When designing a small-scale system for the developing world, it is important to design a system that fits the needs of the community or household based on 1. The type of waste being treated, 2. The volume of the digester. This will depend on the amount of water being produced and the appropriate digester retention time. 3. The location of the digester to ensure that it is well heated, close to the waste production site, within reasonable distance to the house due to pipe length, and away from drinking water sources. 4. The quality of construction materials have to be used to ensure durability of the system. And 5. Implementation, capital, and maintenance costs have to be considered. There are 4 commonly used anaerobic digestion systems in the developing world. The fixed dome digester has 3 main sections. Section 1 is a tank where a mixture of waste and water is poured and flows through a pipe to Section 2, the fixed digester. As the anaerobic process occurs in the fixed digester, the biogas produced creates a pressure that pushes some of the treated waste into a third section, known as the biosolids overflow storage tank. The biogas is stored within the fixed digester, which must be gas tight. A gas pipe is connected to a rigid gas storage tank to allow release of biogas when needed. This digester is low cost, saves space, and can last for up to 20 years. However, due to its under-the-ground design, it has low temperature, needs skilled labor for maintenance and construction, and has pressure issues. The design of the floating drum digester is very similar to the fixed dome digester, but has a moving gas storage tank. The floating drum is supported by a guiding frame, and the tank rises and falls depending on biogas production and use. The drum floats on top of the digesting slurry or on a water jacket. Materials such as plastic reinforced with fiberglass and high-density polyethylene can be used for constructing the drum. Unlike the fixed dome digester, this digester has no pressure issues, does not require skilled labor, and preferred by users because they can see the presence of biogas. However, the floating drum section adds cost and lasts for only 15 years due to corrosion from the biogas. Polyethylene tubular digesters, also known as balloon digesters, are constructed from semi-elastic plastic or rubber bags. Tubular digesters are placed in a 2 to 5% slope trench and operated much like a fixed dome digester with a separate biogas storage tank. They cost the least compared to the other digesters, are operated at high temperatures, but are easily damaged and last the shortest time. The basic UASB process is designed to have the wastewater fed from the bottom of the reactor. The wastewater moves through a layer of granular sludge, also known as the sludge blanket, where microorganisms carry out biodegradation. The effluent is released from the sides at the top, while the biogas is collected in a special gas collector at the middle. These systems produce low biosolids concentrations, can handle shock loads, require smaller volume, and can last for a long time without feeding. However, they take the longest time to set up due to the creation of the sludge blanket, may require skilled labor, and can be odorous. The most common use for biogas in the small-scale developing world systems is for cooking.
Besides biogas, the other recovered resource from anaerobic digestion is the sludge portion. In large-scale applications, this material is generally heat or chemically treated to produce residual that can be land applied as a soil amendment. This heat treatment is very effective at stabilizing the sludge and often removes problematic constituents like pathogens. However, in case of small-scale systems, the process of stabilization and disinfection must occur entirely within the digester, as further processing is often not employed. This figure represents the global prevalence of roundworm infections, most of which are occurring within the tropical regions of the planet. Roundworms are interesting because their eggs have been shown to be able to survive for lengthy periods in anaerobic digestion environments. So it brings to question whether small-scale waste-to-energy systems that are installed in these high-prevalence regions are actually producing a safe residual, or are they exacerbating the risk of infection? Let's take a look at how this could happen. As animal or human waste containing roundworm eggs is deposited into the digester, they spend a certain amount of residence time within the digester. This time is based upon the ratio of digester volume to the volumetric flow rate of waste coming in. During the residence time in the digester, the egg will be exposed to reactor conditions that are proven to be not very good at destroying this particular parasite. If the combination of temperature and time is not sufficient, the still viable egg will be pushed out in the residual as the digester is continually fed. Since the residual is promoted as a fertilizer, this infectious blend of solids is vectored right back to the owner through multiple pathways. This situation could be worsened if the system is not maintained, allowing sludge to build up inside the reactor, which reduces the volume and in turn the residence time. Here, at the University of South Florida, we are taking roundworm eggs and exposing them to common anaerobic digestion environments to better understand their fate in these systems. Through the use of microscopes, we're able to determine when the egg transitions from a viable to a non-viable state. We can then use this information to design anaerobic digestion systems to be more culturally appropriate. Ultimately, anaerobic digestion is a good, clean energy option because it can accomplish many of the priorities in a waste management strategy,